In this video, we're going to collect a family of examples of ideals in a ring, and that ring we're going to look at is the integers. So let's set mz to be set for any m in z, mz to be equal to the set of all multiples of m. Okay, so as a set, m has like 0, plus or minus m, plus or minus 2m, plus or minus 3m, and so on. So in particular, let's just use some of the language we learned. If m is 0, then 0z is 0, is trivial, and proper. It's one of those trivial ideals. If m is plus or minus 1, everything is a multiple of plus or minus 1. Then plus or minus 1z, you pick 1z or negative 1z, it's just all of z. So this is trivial but not proper. Trivial as an ideal, but trivial and proper ideal, trivial but not proper ideal. Okay, so now the question is, what happens for other m's? Is it an ideal? Let's find out. So I claim, well, even for these it's an ideal, but for any m, you fix an m, mz as a subset of z is an ideal. So m is fixed. Let's just, m is fixed. You're not allowed to vary m once you've constructed mz. All right, so let's go through and show it. So I claim, so what's the first thing we have to do? We have to show 0 is there. Well, 0 is m times 0, so that's certainly in mz. Okay, great. 2, suppose we have 2 elements in mz. What does it mean that we have 2 elements in mz? Well, there exists some k and l in z such that x is mk, so it's some multiple of m, and y is ml. Then x plus y is mk plus ml is m times k plus l, because z is a ring, so the distributive properties hold. And this is a multiple of m. Great. So it's closed under addition. And now we need to check it's closed under multiplication by z, or it absorbs multiplication by z. So we're going to suppose that a is in z and x is in mz. Then, like before, there exists some k in z such that x is mk. Then ax is a times mk is m times ak is in mz. But z is commutative. Well, I mean, not but and z is commutative. So xa, which is equal to ax, is also in mz because ax is. And when you have a commutative ring, you only have to check it absorbs multiplication on one side. You don't have to check both sides because it's redundant, because it's commutative. Great. So it absorbs multiplication by z, and so therefore it's an ideal. So you pick your favorite m, you look at multiples of m, that is an ideal. Okay, so we have a nice infinite collection of examples. One for any, for any integer you pick, we have an ideal. These aren't unique though. We saw actually that plus or minus 1 both gave rise to z, which was a trivial ideal. So let me just note here in cautionary orange. mz is the same as negative mz. because the multiples of m are, of course, the same as the multiples of negative m. And so, although you have a ideal for every integer, they're not unique. You really only have an ideal for a distinct ideal for every natural number. Okay. And I want to also notice one thing here. So if this is labeled a theorem in the book, but it's not. There's hardly any proof here. So for any m bigger than 1, this actually is true if m is not bigger than 1. It's just true for any m. But it's stated for any m bigger than 1 because this is the only time where it actually has some content. The reduction modulo m homomorphism phi from z to z mod m, defined by phi of x is reduced modulo m, has kernel mz. So in particular, we were trying to generalize kernels with ideals. And in fact, we showed that these ideals that we get here, I'll prove this theorem here in a second, this ideal that we get here, these mz's from our example from before, they're actually already kernels. And we're going to show that this is always true. Ideals are always kernels. At least two-sided ideals are always kernels. And this is a general fact. This is a general fact. So so let's prove this theorem real quick. And all this is saying is, hey, those ideals that you constructed, they're actually kernels. Okay, so proof. This is again not hard. Suppose phi of x is 0. Then what do we know? Well, x bar, which is phi of x, is 0 bar. So x minus 0 is divisible by m. That's how you are 0 in z mod m. There exists some k in z such that x, which is x minus 0, is mk. So x, which is mk, is certainly in mz. Okay, so this tells us then the kernel of phi, the reduction modulo n map, is contained in mz. And now we have to do the other direction. So we have to suppose that we have suppose we take mk in mz, we have to show that it's in the kernel. Then phi of mk is reduced modulo m, but that's m bar k bar, but m is 0. And anything times 0 is 0. So mk is in the kernel, and we conclude that there must be equal to the kernel. Why? Well, we showed a double containment argument, and that's the end. And this is a general fact that we're going to see is true. All ideals are kernels, and we know already that all kernels are ideals, but actually the converse is true.